Welcome. After learning the various types of balance equations, now we shall be looking into the various ways of the data analysis, and we have learned something about the methods of solution. Now, many times you find that when you have the model equations with you, you need to know some of the values of the properties or some coefficients like heat transfer coefficient, mass transfer coefficient, etc. from some given data. The data may be given in terms of some correlations and sometimes in terms of some tabular form. Now, in many cases you find that the exact data are not given to you, and in those cases you have to use some kind of mathematical ways to find out those missing values. So, in that respect we need to learn what are those mathematical techniques, and many times we also want to know the effects of the various variables on the process. For example, if you are doing some heat transfer experiment or heat transfer analysis, you find that either you can find the effects of the say flow rate on the heat transfer performance, and sometimes you need also to figure out that what is the say effect of you are given some kind of say data say versus flow rate versus the some performance of the process. So, you need to know that what kind of effect is there in terms of that, whether it is linear effect, whether it is nonlinear effect. If there is nonlinearity, then what kind of nonlinearity is there in the effects. So, all these things can be understood if we do some analysis mathematically. So, in this context, first we shall be looking into the regression analysis. So, in this particular thing we shall be looking into linear regression, then polynomial regression and exponential regression. So, first let us understand what we mean by regression. Regression means that we are trying to determine the relationship between the various variables involved in a process, and these variables will be given in terms of some experimental data. Now, when do we need to know these relationships from the experimental data? Is this that many times we may not have a proper theory to correlate the variables, or many times we find that even if there are some theories, but the theoretical expressions become so complicated and complex that we are not able to adopt them in our analysis easily, and sometimes we also do not need to have the exact theoretical expressions. So, in those cases we try to just figure out that what are the primary variables which are of our concern in a given analysis, and from those values of the variables we try to adopt some simplified way of correlating these variables, and that is what we do with regression. So, in this way what we find that this regression helps us in analyzing and understanding the effects of the process variables easily. Okay. Now, examples are like, for example, we want to know the effect of the temperature or pressures on the various material properties like density, viscosity and other properties. Like in this case we do not need to always carry out the experiments, or we do not need to go into the theoretical analysis. Just by taking some kind of experimental data at some specific points, we can regress those data, and by that we can also find out the values of the particular properties at some other values of the temperature, pressure which are not given to us. And in another example, that for example we need to know the effects of flow rate. Generally flow rate comes in through the Reynolds number on the heat and mass transfer coefficients, which are again generally come through Nusselt number and Sherwood number. So, here you will find that if somebody might have carried out some experiments, in those experiments somebody might have reported the flow rates, and with each flow rate they might be reporting the values of these coefficients values, and then what you do that you find out the Reynolds number from those flow rates, and then you convert these coefficient values into either Nusselt number or Sherwood number, and then try to regress these values so that you can obtain a generalized correlation which will be having a more universal validity. Now, I told you in my earlier lecture what is the importance of putting the variables, process variables in terms of the non-dimensional numbers. Now, this regression is generally done by finding some mathematical expression to correlate the data points. Now, these mathematical expressions could be algebraic expressions. For example, we can have linear expression, we can have quadratic expression, or we can have some polynomial, or they could be transcendental. Transcendental means it could be say exponential, kind of logarithmic, or say hyperbolic. So, all these kind of expressions are called transcendental. So, we can have either algebraic expressions or transcendental expressions to correlate these data. So, despite all these simplifications being provided by the regression, we find that they have some limitation, and limitation comes because we are taking a fixed number of data points to understand the behavior. Now, that the whatever regression after regression we are finding the correlation, we find that those correlations will be valid within the range for which we have taken the data, and anything outside this range, if we want to predict, will be a bit could be erroneous if we find that there is high nonlinearity. Now, if there are linear expressions, then perhaps we can extrapolate to some extent, but other than that, if we find that there is some highly nonlinear behavior of the two types of variables, then we should be careful not to extend or use this regression expression for outside the domain of our determination. Now, here we show that how mathematically how we represent it or graphically we represent it. So, let us see that we have two variables, one is x and there is y. Now, x is what? X is that dictates the values of an dependent variable y. So, x is taken to be the independent variable and y is taken to be the dependent variable. Okay? And generally x can be the measured variable. For example, we can measure temperature, we can measure flow rate, etc. can directly. Okay? And y is the variable which is obtained indirectly. That means, for example, if we are talking about specific heat, then specific heat cannot be obtained directly by measure by any kind of sensor, but it has to be obtained by indirectly by combining the various types of properties or the measured variables like temperature, pressure, etc. Okay. Now, what we do that now we plot this y versus x here, and suppose these dotted points are the values of this at each x point or the value of y. Then what we do by regression, we find some kind of curve which is passing through somewhere between these points. It is not joining the points, but it is passing somewhere between these points. And then this particular curve, which is called y in terms of x, this particular curve is obtained after we do the regression analysis. Now, we shall be looking into this concept and try to understand it by some examples now. So, when we say that we have to regress, what we mean that we have to find the best fit. Now, best fit means that various ways we can define the best fit. Here in this example, for example, you see that this particular these 2 points are the actual data points. Okay? And suppose through this we are sort of taking this regressed curve, and what we say that let us see that define some error. The error is that between the regressed value that is coming from here and the actual value. Okay? So, if I say that the actual this regressed value minus actual value, in this case we find this is coming to be negative, because this is regressed value is less than the actual value, and similarly in this case we find that regressed value minus the actual value is coming out to be positive. So, what we are trying to do that we are trying to minimize the summation of the errors. That means, whatever for say there are n number of data points, for each of the points we are finding the error between the regressed value and the actual value, and we are summing up the errors and we are trying to minimize the total error. Now, in this case what we find that the errors could be negative and positive, and many a times these negative and positive values may get cancelled, and if they get cancelled, it would look as if the total will be 0. In that case, it would look as if there is it is this regressed value and the actual value are matching perfectly, but that is not the case. So in that case, we have to devise some other way. One way is that we minimize the total of the absolute value. So here we have that we have this absolute value, like we take whether it's positive, negative, we take the absolute values and then sum them up. Okay, this is another way of doing this fitting. Third way is this, that we again find the errors at different regressed points. Okay, and here we show that different regressed points we are taking the errors, and then what we do, we try to minimize the maximum error among all these errors. Okay, so this is called the minimax problem. And lastly, the least square error. In the least square error, what we are doing, we are trying to least square, means we are squaring the errors. For each regressed value, we are squaring the errors. So you see that we are squaring the error here and then summing them up. Okay. So this least square method is a very popular method, and in this particular lecture we shall be looking into this least square method. So let us first understand the principle of least square. I am not going to detail of these things because these are dealt separately in dedicated courses on numerical techniques and statistical methods. So here I shall be just giving you the overview of these methods. So in the least square principle, what we have, that the curve should be fitted through the given points so that the sum of the squares of deviation between the given values of y and the regressed value, say y carat, is minimized. Okay. So that is the meaning, that in this we repetition of this. So here we see that we have the regressed value, say this is the y carat and this y is the actual value. So what we do, we try to minimize the sum of the squares of these errors, and we assume that the x values in the data set, this x1, x2, etc., whatever the data set we are taking, in these x values are not the same, they are different. Now suppose we want a linear regression, that means we say that the y depends linearly on x. So this is a linear expression. You can see that y equal to k naught plus k1 into x. Now what is k naught? K naught is the what we call the intercept and k1 is the slope. Okay. So now you see that if we plot y versus x here, and here we see that this is the line which is the y equal to k naught plus k1 into x. Okay. So this is yj. So this particular one is yj. So yj equal to this, and then we this y is the this y is not the yj. This is the regressed value, that is y tilde. Okay. This y tilde and this is the actual value yj. So what we are trying to do, we see that there is an error between this yj and y. Okay. So this is the regressed expression, this is a regressed curve. Okay. So this particular error, square of the error, we try to minimize. So this is the expression that minimize the sum of the squares of the error. This yj is the we can put the yj prime, this tilde, this yj carat is minus, this is the regressed value, the actual value. So we find the this is the actual value, this is the regressed value, this whole thing is the regressed value. Okay. So we try to minimize the square of the errors. Now whenever we are regressing with some kind of equation, whether it is linear or polynomial, first we have to understand that what is the goodness of this regression. So in that, to understand the goodness, we define something what we call the correlation coefficient, and this is defined like this. Okay. And in this expression we find this is the sxy, this is the sx square, and this is the sy square. So you can see here that these coefficients are obtained from the given values of the data points. Okay. Now what we do, we take this example. Here we have asked that we are given some data set of T versus Cp. Okay. So, T is the temperature in Kelvin and Cp is the isobaric specific heat, and that is given in terms of joule per gram per Kelvin. So, we have been asked to determine a least square straight line approximation for the data set. So, we have to find a linear fit to this data set. So, here we have that we have been, so we put this specific heat in terms of linearly in terms of temperature. So, let us put Cp equal to A plus Bt, and the number of data points is taken to be 8. So, here we have the expressions. Now, I will give a hint to you that how we get these expressions. It is very simple, that you first see that from this expression what you find, that Cp minus A minus Bt. So, this is the error, and this you square and take a sum, and this sum is basically say I to n. Okay. So, this is how it is. Now, if you were to minimize, then this you have to minimize, this thing you have to minimize. Now, minimize with respect to what? Minimize with respect to A and B. Okay, that means you have to adjust this A and B value so that you can minimize this error. And what to do that? What we do that, as we have learned in calculus, to minimize we have to take the first derivative first to take it to be 0. So, suppose I define this expression as some kind of a function in terms of A and B. Now, please understand, we are not defining these functions in terms of t, okay, because at each point of this ti, actually this for each point of ti we have been given the value of Cpi. So, it is function of basically A and B, and this is the function. So, this is the function here, and to minimize this error function, what we do, we first take this dou f by dou A equal to 0, and then what we do, dou f by dou B equal to 0. So, you do this too. You can do this exercise very easily. You find the derivative of this error function with respect to first A and then with respect to B, and equate them to 0. Once you equate them to 0 and rearrange them, you will find you are getting this particular expression and this expression. Now, this expression you will find, this will come, because you will find that this thing will come, that you will get something like this, I equal to 1 to n. So, from that you will get this A is coming out, and you will get A into n. Okay, that is how you get the expression, and rest of the things you can find out easily. So, you see that we are taking these A and B out of the summation, because they do not depend on the ith, the value of the particular coefficient. And now, you see that we have two expressions, and in these two expressions we know the temperatures, we know the specific heats. What we do not know are the A and B values. So, we have two unknowns and two equations, and now from these two unknowns and two equations you can easily find out the values of the A and B. Okay. So, this is how we will we are going to solve these expressions. Now, after understanding this, now what we do, we get all these values of these summations of temperature, the specific heat, and the square of the temperature, and it will be this will be Ti into Cpi. So, this summation of the products we get, okay, and after obtaining all these, we put them in these expressions which found earlier, and from these two equations we solve for A and B, and these are the values of the A and B. So, now we find that the linear fit, the linear expression which is fitting this specific heat with the temperature comes out to be like this. Okay. Now, whenever you are using any of these fitted equations, one thing you must be very careful about is this, that whatever units you have used to regress, they must be maintained whenever you are going to use this expression in future for any kind of determination of the Cp or the dependent variable. If the temperature is supposed in centigrade or Fahrenheit, okay, you must first convert them into Kelvin, okay, to get the value of Cp. If you make any mistake in using the proper units, you are going to land up with wrong answers. So that you should be very careful about whenever you are going to use any kind of regressed equation. So here we see that after regression, whatever values of the Cp we are obtaining, so we are putting those values here. So this is the solid line shows our regressed expression, and these points are the actual data points. Okay. Now we put in this table the temperature values, and here we put the exact or the given values of the specific heat, and in this we are now getting the values of the Cp, which we are calling approximate, because how we are getting these values? We are again putting these temperature values in the expression we have just obtained, and from that we are getting the values of the specific heat. So here we are putting the specific heat values, and after that what we are doing, we are trying to find out the percentage error. That means this approximate value minus this exact value and take the absolute value. Okay. So this, for finding this percentage error, what we are doing, this is nothing but this mod of this exact minus approximate and divided by the exact into 100. Okay. So this is how we are able to get the percentage error. Understand one thing, whenever you are finding the percentage error, it must always be found from the exact value. With respect to the exact value, what is the error? You never put here the regressed value, okay, not the approximate value. Okay. So that is, and we see that after we make this error analysis, what we find that there is a good matching, means the maximum error is coming to about 0.97%. Okay. So whether it is negative or positive doesn't matter, but what we are finding, it is coming very small. So that is how we can say that our regression or this assumption of a linear fit between the specific heat and the temperature seems to be okay. Okay. Next we take another example. Here again we are given a set of specific heat as a function of temperature, and this is given for high temperature and the same air. Okay. In the last problem was at low temperature, this is for high temperature, and again we find that here temperature is in terms of Kelvin and the specific heat is in terms of joule per gram per Kelvin. Okay. Now we have been asked to find the least square quadratic polynomial. So what we shall do, that now we shall do this expression, get this expression. We assume that Cp equal to A plus Bt plus Ct square. Now in this case, as I told you earlier, what you can do is that you can simply again put the error function, and now it will be in function of A, B and C. Okay. And this you take to be like Cpj, which is given to you, minus A minus Btj minus Ctj square, and j is equal to 1 to n. Okay. Now what you do, you simply find, now this expression has been obtained how? This dou f by dou A is equal to 0. Then this expression has been obtained from this dou f by dou B equal to 0, and this expression has been obtained like dou f by dou C equal to 0. Okay. So by doing this, you get these three expressions and you find that these three equations, and we have three unknowns, that is A, B and C. Okay. Now once you get these equations, it becomes now easy for you to solve these equations, and you can get the values of A, B, C. Now you see that as we keep on increasing the degree of the polynomial for regression, we find we will be having still more number of equations, And when you have so many equations, what you can do is this: you can use any of the methods which we have learnt earlier, matrix methods, to solve up to say third degree, second degree polynomial, where we get 3 equations. There perhaps we can do it by manually, but as the number of equations increase, then you have to use an efficient matrix methods, and sometimes you have to go for some coding to solve these expressions. And these two for these codings, it is always preferable that you can develop your own coding, so that you also develop some coding skill. That always helps you. Otherwise, you can also use the standard packages like Excel or MATLAB to solve this set of equations. Now, let us see how they will look like. Now, here you see that we are finding the values of the various summations involved in the given equation, and then after plugging in these values, we find that we are getting these 3 equations, and from these 3 equations, by using the Gauss elimination method, okay, we are able to solve for this A, B and C. Okay. And now we get the regressed expression for Cp in terms of the temperature. Now, whenever you are getting all these regressed expressions, one thing you understand that they are just simply giving us the dependency of the dependent variable on the independent variable, but they are not telling us anything about the physics, means why they should follow this kind of pattern. These are not there whenever we are going for regression. Okay? But these just help us whenever suppose you are going for some simulation. So, you can quickly take these values either from some data table, regress them within the range of your interest, and they will help you to quickly do the simulation without going into the physics of the particular process. Now, here we find that we again plot the regressed value along with the actual values which are given to us, and like earlier we find out the percentage error. So, here we find the percentage errors, and here we also see that this quadratic regression gives a quite good fit, and the maximum error which is there is only about 0.29%. Okay? So, that says that the regression is good. Should I go? Hello? আচ্ছা আমি আরো 5-10 মিনিট নিতে পারবো এটাকে কন্টিনিউ করে আচ্ছা ঠিক আছে হ্যাঁ Next, we take this particular expression. In this problem, we have to go for a power law regression. What we mean by this will be clear to you. Now, first let us see that kind of data set which have been given to us. That is, we are given the pressure, and at each pressure we are given some flow rate through a hose. Okay, and we know that whenever in a hose is a some flow rate is going on, we can find out the flow rate in terms of the pressure drop. Okay. So, here we are given that pressure drop, you can say, as if and for each pressure drop we are given the flow, and again you please take care of the units. It is gallons per meter and pressure is in PSI, that is pounds per square inch. And we have to find a least square power law approximation. So, what we mean and how to express this power law approximation? For that, let us see this, that we put this is power law, that we put Q, that is the flow rate, as function of A equal to P to the power B, and here we have this N equal to 5. Okay. Now, to put this in terms of our least square, so that we can solve it in a linear fashion, what we do, we take the logarithm of this whole thing from both sides. So, we take natural logarithm. So, here we find that ln q equal to ln of A equal to B plus ln of P. Okay. Now, you see that we replace this ln of the, that means natural log of the flow rate, as y, and then logarithmic of A we take as A, and logarithm of p we take as x. So, we have this equivalent expression, that is y is equal to a plus bx. Now, whatever we have done earlier to do a linear curve fitting, we apply the same method. Only thing is this, from the given table, first we have to find out the logarithm of q and logarithm of p, and we shall be regressing between log q and log p. So, here this x is representing log p and y representing log q. So, here we have the solution that p q we first write from the given data, then we find the log p value over here, then log q value over here, and this is x, this is y, we find the x square value and the xy value, and these are the summations which are needed to find out the values of the a and b. And here we have these two equations in terms of a and b, and here we get the value of a this and b this. Now, a we know that this capital A which is there in the original expression, so that is equal to exponential of this small a which we have found out, and this is coming out like this. So, that is, now we find that q is equal to this a value here and p to the power b, that is 0.491. So, here we are putting the regressed curve here, and these are the data points given, and we find that it is not a linear. Okay, when we are plotting in a linear scale, it is not linear, but if we plot this p and q in a log scale, then we shall find that this will come to be a linear curve. Okay, that is the difference. So, here we find that it is not a linear curve, it is kind of an exponential curve which we. So, these are the references which you can look for more detail of this kind of techniques. Thank you.